Okay, in this demo, I'm going to give a walkthrough of keras tensor neural network tutorial walkthrough. Just like usual, in the first cell, we import all the required libraries, and then this cell demonstrates all the common ways to create a TensorFlow tensors from Python list using tf dot and all those, and this is the output. Next, here I list all the common required D types as we have seen before, like float 32, float 64, and all the ones which we see here. And in the next one, cell lists all the available physical devices, shows how to place tensor on specific devices using a tf.device context manager. In the next cell, I demonstrate the core TensorFlow tensor operation, element wise all the arithmetic operators. Okay. In the next one, we cover all the TensorFlow reshaping methods, which is reshape, transpose, dims, and squeeze. In the next cell, I explain the critical difference between constant and immutable and cannot be updated. And TF variable, which is mutable, represents a trainable parameters. In the next cell, it introduces ensum with a series of increasingly complex examples, starting from basic operations like transpose and row sum. In the next cell, I use ensum for dot products, outer products, element-wise multiplication, and matrix multiplication. Next cell applies ensum to batch matrix multiplication, where B is the batch dimension. Next cell, I print a complete reference table of ensum notation alongside their equivalent TensorFlow operations. In the next cell, introduces a gradient tape TensorFlow mechanism for automatic differentiation. In the next cell, I build a multi-step computation graph inside a gradient tape context and trace gradient back through the chain. In the next cell, computes gradient for a vector variable by computing the sum of squares inside a tape and calling tape.gradient. Next cell, I demonstrate a key gradient or tape patterns, watching constants with tape.watch using a persistent equal to true to compute multiple gradient from one tape, computing higher order derivatives with nested tapes. Next cell demonstrates how decorating a function with a tf function compiles it from Python eager execution into a static TensorFlow graph. Next, here I manually implement gradient descent using gradient tape to minimize a parabolic function and plot the optimization path. Now in the next cell, we re-implement the four main activation functions: sigmoid, tanh, relu, and leaky relu. Next, I implement MSE loss for regression and binary cross entropy loss for classification using raw TensorFlow operations. Next, this cell builds a complete neural network class using only TF variables for parameters, TF gradient tape for gradients. Next, here I train the primitive TensorFlow network on the solved problem, which requires a non-linear decision boundary. Next cell introduces layer dense as keras built-in fully connected layer and inspects its automatically created kernel and BIOS parameters. Next cell, I build multi-layer neural network using keras, sequential by simply listing layers in order. Next, this cell builds a network using keras function API, where you explicitly pass tensor through layers and then create the model by specifying inputs and outputs. Next, I define a custom model by inheriting from keras.model, implementing both init to define layer and call to implement the forward pass. Next, this cell demonstrates the keras training workflow. Next, I define a create MLP helper function that dynamically builds a fully connected network of any depth and width from a list of layer sizes. Next, in the next cell solves the solved problem using keras. After that, we generated two moons data sets, build a deeper classifier using the dynamic MLP builder. After that, the cell plots the decision boundary learned by the moons classifier by generating a denser mesh grid. Next, here I load the sklearn digits data of 8x8 handwritten digit images, standardize future, and train the multiclasser with a 10 softmax output neurons. Then next cell displays a 3x5 grid of test digits images alongside their predicted and true label using model.predict. Next, I demonstrate keras callbacks, early stopping that halts training when validation loss stops improving. Next, this cell prints a side by side comparison table of all three approaches used in the notebook: NumPy from scratch, Tensor primitive with gradient tape, and the Keras high level API. Next, I print a detailed comparison table between Keras and PyTorch across multiple dimensions: execution model, training API, debugging experience, and etc. Next, this cell prints a structured list of best practices covering data processing, model design principle, training stability tips, and evaluation strategies. In the last final cell, this cell prints a comprehensive TensorFlow and keras cheat sheet covering tensor creation, gradient tape pattern, all three models build approaches, the compile and a fit API, and common callbacks. That's it with this demo. Thank you.